Okay, Organic Chemistry 1. This is section 5.7, which deals with Fischer projections. And we looked at Fischer projections briefly in chapter 2 when we talked about a Haworth projection, Sawhorst projection, Fischer projection. So again, a Fischer projection can be used to represent molecules that have chirality centers. Okay, so um, the horizontal lines in a Fischer projection, and this is a correct Fischer projection, the one that I have down here in the yellow circle. The horizontal bonds or lines, what they represent are bonds that are coming towards you. So, like my student said, it's like the molecules trying to hug you. I wasn't the one who invented that. It was my students. I just thought it was so great. And then the lines that are vertical, it's as if they're going back into the page. Okay, so we have the lines going back into the page, and then we have the lines coming out towards us in the Fischer projection. So, like let's say you look at a molecule like glucose, and there isn't really a lot of room here to draw the glucose molecule. But again, I know that some of you are biology majors, so you would have seen glucose show up, when you're discussing the Krebs cycle or glycolysis or something. If we look at glucose, you see that glucose has 4 chiral centers. 1, 2, 3, 4, like that. We have a hydroxyl here, here, and here. Glucose is one of the few carbohydrates that I have memorized. Okay, so this is what we call D-glucose. And the whole idea behind the letter D, you'll learn that in organic chemistry too. But you can see that there are 1, 2, 3, 4 chiral centers here. And if you look at the molecule that they've shown here in the slide, is that there's 1 chiral center here. And the thing that they have in common is that you notice that the hydrogens, right, all the hydrogens in glucose on the chiral centers, and the hydrogen on this molecule is on a horizontal bond, which means it's coming out towards you. Well, what did we do when we were assigning the RNS designation to a chiral center if the hydrogen was coming out towards us? We reversed it, right? So you're going to see the same thing when we look at chiral centers with Fischer projections. So let's move on. It says Fischer projections are most useful when drawing a molecule with multiple chirality sugars or multiple chirality centers like sugars, okay, shown below. Now, again, that's something that we cover. We look at carbohydrates a lot in chemistry 3111. However, we look at the chirality designations in chemistry 3101. So basically, in organic chemistry 2, you do a whole chapter on carbohydrates. But the reason that Emil Fischer developed the Fischer projection, there's actually a very good reason, and I'm not going to get into a lot of the details on the history, but it's that originally when he was drawing the structures of things like glucose and fructose and mannose and ribose and aldose and ultrose, whatever, is that he was using the zigzag formula like that, and then he'd put CHO, and then he was trying to write all the chiral centers as dashes and wedges, and it got really confusing really quickly. And so he developed the Fischer projection because it was a much more rapid way to communicate the structures of sugars that have so many chiral centers. Okay, so many chiral centers, it gets daunting, it gets cumbersome. And so that is why the Fischer projection was developed. So let's say we wanted to look at the 2 chiral centers in this molecule here. We have one here, and then we have one here. I just want to show you how to determine the stereochemical configuration at these chiral centers before we move on. So let's take a look at the one highlighted in yellow. What are the groups that are attached to it? I've got a hydrogen, that's going to be the 4th priority. I've got an oxygen, that's going to be the highest priority. Then here I have a carbon, and here I have a carbon. Well, the carbon on the top, since it's got a carbonyl, it's attached to oxygen, oxygen, hydrogen, whereas this carbon down here is attached to oxygen, carbon, hydrogen. Oxygen, carbon, hydrogen. And so you can see the point of difference is right here. It's the oxygen. So that means this is going to be our 2nd highest priority group, and then all of this down here would be the 3rd highest priority. So we'll put a number 3 down here. Now here's our chiral center, so we go around the chiral center from 1 to 2 to 3. I am going counterclockwise, right? And if I'm going counterclockwise, but this bond is coming out like this, that means I reverse it. So instead of being S, this chiral center that I have highlighted in yellow would be R. So let me erase all this spinach here, and I'll write R, and then we'll try the next one. So here we have an R, stereocenter. So let's see if we can figure out this one. Same technique. Look, this is going to be the highest priority. This will be the lowest priority. This carbon here is attached to oxygen, hydrogen, 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 and this carbon is attached to oxygen, carbon, hydrogen. So this is going to be priority number 2. This will be priority number 3. We go around the chiral center from 1 to 2 to 3. We are going clockwise, which is R. But remember, the hydrogen is coming out, and so we reverse it. So this chiral center would be S. So we have R for the top one, and then we have S for the bottom one. So R and S, like that. And that's how we determine the stereochemical configuration at a chiral center. And you can try it with these ones if you want. I don't have the solutions, but there's some good practice problems in our textbook. What's cool about Fischer projections is that it makes it very quick to assess stereoisomeric relationships, right? If you look at these two compounds here, right, it's very quick to assess that these are mirror images, right? You can see very quickly that these are enantiomers without looking at any dashes or wedges. We don't even have to take that into consideration. You just see that these are mirror images, right? If you look at these two compounds and look at their stereoisomeric relationship, you can see that these two bromines are mirror images. However, here, this is not a mirror image, and therefore the definition must be non-superimposable, non-mirror images. Therefore, they are diastereomers. All right, so that's also very handy when we use Fischer projections. Well, I showed you how to determine the stereochemistry at a chiral center in a Fischer projection. I would like you to try to do the first one here, and then we'll try to do this one here. So I'll give you a second. If anybody could determine the stereochemistry of the one that I have the red circle or the red arrow by, and then the one with the blue arrow. So we'll start with the one on the top. Could anybody determine if that's R or S? And just feel free to type it in the chat, or if you just want to unmute your mic, that works too. All right. Yeah, I see that somebody put R. Yep. Yeah, exactly, Kelly. It's R for red. I think you're 100% correct. Let's take a look. So what she said is, okay, well, the hydrogen's going to be the lowest priority. Nitrogen's top priority. This carbon is oxygen, hydrogen, hydrogen. And this carbon is attached to all 3 oxygens. So here's the tiebreaker. That means that, let me erase this. That means that this is going to be second highest priority. This will be third. We're going from 1 to 2 to 3. Remember, we're going around the chiral center. That would be S because we're going counterclockwise. However, remember, the hydrogen is coming out towards you. And so this stereocenter is, in fact, R. We have the R stereochemical configuration. Let me erase some of my information here. Yeah, I'll just erase this here. What about the one in blue? Anybody get that one? And I'll give you a second to think about it. All right, cool. Yeah. Yeah, I see my students are saying S. I tend to agree. Look, if we wanted to do it really quick, and I am not a fast, I'm not a speed guy, okay? But remember, this hydrogen, where's my blue pen? Your hydrogen is coming out like this. So look, you've got 1, you've got 4, you've got 2, and you've got 3. So you go from 1 to 2 to 3, that's R, therefore it must be S. Just like that. If you want to know how did I determine 2 and 3, remember that this carbon, I'll use the green pen, is attached to oxygen, oxygen, hydrogen, and this carbon is attached to 3 hydrogens. Right, so obviously this is the tiebreaker here. And there you have it. That's the second highest priority. Bada boom, bada bing. All right, here we go. So hopefully you're feeling a little more confident in your ability to apply the Kahn-Ingold-Prelog rules and assign the stereochemical configuration at a chiral center, whether we're using dashes or wedges, or whether it's in a Fischer projection. And of course, I'm going to ask you some questions about that on your next quiz. What's the best way to get really good at this is just repetition, right? Practice, practice, practice. And I promise you will get better and better and better if you just keep going at it, right? Keep going, given more and more practice time, and you'll get even better at it. Well, I want to show you something that I think is really interesting. Okay, like I said, section 5.8 is kind of a quick section. I think I only have two slides on it. It might be worth the value of one multiple choice question on your next quiz, but I want to show it to you because it's one of the just most interesting and fascinating things in the world of organic chemistry, in my opinion. Okay, something that I always think is cool when I get here. I just want to show you something here. So you guys remember the Newman projection, right? If I was to draw a butane molecule, right? If I was to just draw a butane molecule, 1, 2, 3, 4. Oops, I don't know why that happens. 1, 2, 3, 4. Okay, this is a butane molecule. Okay, now if you were to look down the carbon-carbon bond, okay, I mean, one of the Newman projections that you could draw would be to have the methyl pointing straight up like this, and then 2 hydrogens here, and then the other one, have the methyl going down like this, right? That's the anti-conformation, so anti, okay, that's one. But you remember that there's 2 gauche conformations that you can have? Yeah, there's 2 gauche conformations here. Okay, and here we see 2 gauche conformations. Now, I know, and you know, right? We all know that there's free rotation about this bond, okay? And if I was to ask you, are there any chiral centers in butane? And you said no, I'd say you're right, okay? There's no chiral centers in butane. However, the conformations here, okay, and I'm not talking about, specific carbons. I'm talking about the actual whole dang conformation here and this whole one here. If you look at them, you notice something peculiar about them. They're mirror images, okay? So the conformations, notice that it's italicized, right? The molecule isn't a chiral molecule, but the conformation itself, the Newman projection, if you could just get the molecule to stop like this, it is an enantiomer of this conformation. Kind of crazy, right? So the 2 conformations are chiral, number 1. They're non-superimposable upon their mirror images, or they have a different arrangement of the atoms in space, and they're actually enantiomers of one another, right? So we call them rotamers because all we did was rotate this sigma bond right here. So because these rotamers are interchangeable because of the bond rotation, butane is not a chiral compound. It's the conformations that are chiral, not the molecule, just these specific, this picture and this picture, okay? Those 2 Newman projections are enantiomers of one another. Well, what about cis 1,2-dimethyl cyclohexane, right? And you can see it drawn right here, and I'll just redraw the compound here. If you were to draw, let me draw it like this. If you were to draw cis 1,2-dimethyl cyclohexane, and you drew it with a wedge coming up here and a wedge coming up here, right? And we did that earlier today. We said, hey, there's a plane of symmetry down the molecule. Therefore, my friend, it is a meso compound, even though there's chiral centers. But what's crazy is that if you look at the chairs, right? What if you look at both conformations of the chairs and you see that they're going to be equally abundant, right? Because in each one you have a methyl axial, in each one you have a methyl that's equatorial. But what do you notice about these 2 ring flips, these 2 conformations? They're mirror images, right? If you just look at the actual conformations inside this yellow box, you see that there's a plane of symmetry. You see that they're mirror images. So again, with this specific molecule, right, it's not abundantly clear here, is it? Right? You'd never see it unless you drew a chair, but the 2 conformations are enantiomers. All right, but again, since they're in equilibrium, right? It's an achiral compound because it possesses the plane of symmetry. So it kind of depends on how you look at it. So the whole point behind 5.8 is nothing more than you should understand the concept that conformations can be chiral. Just a conformation, right? It says here that this conformation, right, each of this one and this one, they're both chiral. Why? They're non-superimposable on their mirror images, right? These conformations are chiral. Why? They're non-superimposable upon their mirror images. They don't fall under the umbrella of R&S, right? Using that stuff, using the Condon-Gold pre-log rules to differentiate between, two enantiomers, one's R, one's S, okay? We're not doing that at all. It's something completely different. That's why it's got its own section. But the actual conformations are chiral themselves. Give me a thumbs up if you just follow me on the concept of a conformation can be chiral. Just a conformation. I know the molecule isn't chiral, but just the conformations. And it's just these two specific examples, really, that are covered in the book. All right, cool, great. Yeah, just the conformations, and that's it. And I know that all of you are, pondering taking organic chemistry for chemistry majors now because you love organic chemistry so much. But I've taught that class, and we go into a little bit more detail in that class. But really, all you need to know for Organic Chemistry 1 is that, that the conformations can be chiral, which is pretty neat. Well, what we do is we skip section 5.9, which deals with molecules. So molecules that are chiral, but don't have any chiral center. So if you're like, well, how could that be? You could read it. It's really short. Doesn't take you a long time. It's basically because of the compound being locked in one conformation, and you can read about that. Again, very quick, but it's not covered on our quiz. It's not covered on the final. The next part deals with resolution of enantiomers. That's something that I could talk about for a while. I am not I guess I know enough about resolution of enantiomers. I've done it a few times myself when I was a bench chemist. But it's just a way to separate enantiomers. But nowadays, if you want to separate enantiomers, it's very difficult to do. But nowadays they have new techniques to do the separation of enantiomers. And so you can spend some time taking a look at that if you want to. Well, the last section of chapter 5 deals with a new designation that we need in order to provide a name for an alkene that cannot be designated as cis or trans. If you remember, cis and trans, when we talked about alkenes and we looked at cis and trans quite a bit, the only time you can use cis and trans is when you have two substituents on each carbon that are identical, right? Because X is the same as X, those are trans, right? Because X is the same as this X, these are cis. Okay, but if you had four substituents, let's say you had X, Y, Z, and then over here you have A. Well, there's no designation as cis or trans here because none of the groups are the same. So let's say you had an alkene like this one here. You can't label that as cis or trans, right? It's inadequate. Okay, same thing here. It's not cis or trans, but you can see that these are different compounds. Why? Because if you look at them, if you just look at the carbon-carbon bond, so I'll highlight one in blue, and then I'll highlight the other one in red. If you look at the difference between these two compounds, you see that the carbon in blue, the ethyl group and the fluorines are both on the same sides in both molecules, but you see that the hydrogen and the amine, the NH2 group, on the carbon in red have switched positions. So what's the relationship between these two molecules? They're not enantiomers, but they are stereoisomers, therefore they're diastereomers, right? Well, how do I designate them? How do I differentiate between these two molecules when I go to name them? I can't call them cis and I can't call them trans. So what you use is what's called E and Z designation. Okay, again, and I'm repeating myself, but the cis and trans designation only works when there is a like group on each carbon of the alkene. All right, so how do we determine whether something is E or Z? It goes right back to atomic number, right? The periodic table, just like in the Condon-Gold pre-log rules. What we do is we look at each one of the carbons. So the first one was the blue carbon. Okay, the second one was the red carbon. We look at the atoms that are attached directly to each carbon. Okay, So if we just look at the carbon in blue, it's got what? It's got a carbon attached to it and a fluorine. What's got a higher atomic number? Well, fluorine is element number 9 and carbon is element number 6. Therefore, the fluorine takes priority. I go over to the red carbon. What are the atoms attached there? I've got a hydrogen and a nitrogen. Well, nitrogen is element number 7. Hydrogen is element number 1, of course. So there you go. So these two higher priority groups are on the same side of the molecule. Okay, they're on the same side. And so we say that they are E or entgegen, which means together. So the top priority groups, when they're on the same side of the carbon-carbon double bond, it's Z for zusammen. Did I say E when I meant Z? Sorry, I don't know. Maybe I need another drink of coffee. Anyhow, so what I meant is that these are on the same side. So they're Z, which is zusammen or together in German. I did study German. And then if they're on the opposite side, they're E or entgegen, which means opposite. Sorry if I misspoke. Sometimes my students tell me it's E for opposite. Anyhow, something that they students might find beneficial. So again, how do I differentiate between these two alkenes? This one is a Z compound because the two higher priority groups are zusammen, together, that's German. And these two high priority groups over here, they're on opposite sides. So it's E for entgegen, which is German. In fact, a number of years ago, and not that long ago in history, maybe 30 or 40 years ago, in the 1980s and 1970s, if you wanted to get a degree in chemistry, you actually had to study German. You had to study probably second or third year German. And the reason why, if you're like, what does German have to do with organic chemistry or chemistry in general? It's because there were a lot of important journals, namely Beilstein. So I don't know if any of you have heard of it, but Beilstein is an important journal that was published only in German for many, many years. So if you wanted to look up a procedure or look up something, you know, in that journal, you had to read German. In fact, the lab that I worked in when I was in Canada, one of the labs I worked in, I worked with a guy who spoke German. And every once in a while, wasn't often, but every once in a while, somebody would show up in his lab, and I was in his lab, and they'd say, hey, I have this procedure in German, and I can't read it. Can you tell me what it says? You know, and he'd be like, yeah, it says stir this for this long, and then do this or whatever. Anyhow, let's take a look at a practice problem here. This is question 5.29. Comes right out of our textbook. And it just asks you to do nothing more than designate the configuration of each double bond as E or Z. I'm just going to go with it, you know, and throw this out there to my students. So the first one, I'll label this carbon in, son of a gun, I'll label this carbon in blue, and I'll label this carbon in red. Could anybody solve A and tell me if it's E or Z? And we would use the same Kahn-Ingold pre-log rules to designate a higher priority, right? We would keep looking for a point of difference. I'll give you a second to think about it. If anybody has an answer, of course, just type it into the chat or unmute your mic if you want. Does anybody have an idea about this one or a hunch? I'll give you a few more seconds, then I'm going to take a look at it. Okay, let's take a look at it. So the carbon in blue, we've got, I'll use my black pen. Where's my black pen? Here we go. We've got a carbon here, and we've got a carbon here. Well, which one is higher priority, right? The example that we looked at had nitrogens and fluorines and carbons and hydrogens. Well, we do the same thing we do with the Kahn-Ingold pre-log rules. This carbon is attached to carbon, hydrogen, hydrogen, whereas this carbon is attached to CC, hydrogen. This is the point of difference. Therefore, this is the higher priority group. This one, this isopropyl group. So I'll circle it here. That's the higher priority group. I'm just going to erase some of this to clean it up a little bit. Now on, now on the second carbon, the one highlighted in red, I've got a hydrogen and I've got this sec-butyl group. Well, which one do you think is higher priority? It's going to be the sec-butyl group, right? Because it starts with a carbon. So I highlighted the double bond in yellow. So the two highest priority groups, the isopropyl group and the sec-butyl group. Could anybody tell me, would these be opposite, or sorry, E for opposite, or entgegen, or would they be Z zusammen for together? So since they're on opposite sides of the double bond, it would be E. So the designation here would be E. They are on opposite sides of the double bond. All right, let's take a look at the last one. So we've got our double bond here. If we look at the first carbon, I'm going to highlight it in blue. Okay, we've got a chlorine and a carbon. Well, chlorine has a higher atomic number than carbon, so chlorine's going to be the higher priority. And then I'm going to highlight the second carbon in red. It's got a hydrogen attached to it, and it's got a methyl group. Well, the methyl group is going to take higher priority because carbon has a higher atomic number than hydrogen. So there you go. You can see that the two higher priority groups are on the same side. And so this is going to have the Z designation. It is zusammen, right? These are together, or Z, right? And again, these are on opposite sides, opposite, and therefore they are E, like that.